Okay, so we're going to look at creating a removable partial denture and look at a systematic and logical approach for designing removable partial dentures, be them mucosa borne or tooth borne, bounded saddles, free end saddles, whatever it is. A way of working in a systematic logical sequence to come up with a design. So this is our system of design. So you'll come across this in most of the text. So when we're starting off, you'll see that in a lot of the textbooks they always start by saying that you should survey the model, which is quite right, but for example, if we had this model, would we initially go ahead and start randomly surveying all the teeth? Well, no, we wouldn't. We'd think about which teeth are significant to the design. So we've already made some decisions in our mind, and they are where the saddle areas are, where the teeth are going to go, and what type of denture we're going to make, so whether it be a mucosa borne or a tooth borne. So in our system of design we ought to really acknowledge that to start with. So the first thing that you would do is design your saddle areas. So one, it's the saddle areas, and when you're designing your saddle areas you're looking at the extent of the saddle, how many teeth you're going to be putting on that saddle area, and if it's mucosa borne you may treat it differently to a tooth borne denture, mucosa borne or tooth borne, because if it's mucosa borne you may want to increase the footprint of the denture. But we'll come back to that when we talk a bit about connectors later on. Okay, so you would highlight your saddle area to start with, think about which teeth you're going to be replacing, and then secondly you would consider the type of denture and how you're going to gain your support. Again, this relates to the mucosa or tooth borne, or whether it's a combination of the two. So when we're planning support, you can consider support resistance of movement in the direction of the mucosa, so down towards the mucosa. I always think of it. So support is resistance to movement down towards the mucosa, and if we're doing a mucosa borne denture, then we would look at again the footprint of the denture, and we'd want to make that as large as possible to gain as much support as possible. So this connects with our saddle area, of course, I shouldn't say connect because that's a component part, but linked in with our saddle area. We want to make the saddle area big and the connector big to create a large footprint of the denture, so that spreads the load out as much as possible. If we're doing a tooth supported denture, so tooth borne denture, then we're going to design in occlusal rests, and occlusal rests are the metal components that sit on top of the teeth, typically in rest seats. Okay, and they transmit the load from the artificial tooth, from the artificial tooth through the metal framework through a small metal occlusal rest that sits in an occlusal seat on the surface of the tooth. And we have occlusal rest seats so that they don't interfere with the occlusion, and also to transmit the force down the long axis of the tooth. Long axis of tooth. And when we're designing occlusal rests, or deciding where they should go, there are a couple of very simple rules. So if we have bounded saddles, such as this case, which is purely tooth borne, then we put the occlusal rests as close to the saddle area as possible. Close to saddle area, or saddle, as possible. Okay, now that's relatively logical, because if we're putting load on the artificial teeth here in the saddle area, we have a metal framework that runs underneath the acrylic and to the occlusal rest, and we want that to be as rigid as possible so we keep everything nice and compact and we're not going to get as much flexing in the denture. If we're doing a tooth-borne denture where there's a free end saddle, then this part of the denture is going to be mucosa borne. No matter how many occlusal rests we put on these teeth around here, this is going to be a mucosa borne part of the denture. So really this is a tooth and mucosa borne denture. Okay, tooth and mucosa borne. And there again is a simple rule of thumb that when you're designing your occlusal rests for these tooth and mucosa borne dentures, where we've got a free end saddle, we want to put the occlusal rest distant to the saddle area. So the occlusal rest distant to saddle, and it wants to be at least the opposite side of a clasp tip to the saddle area. So we want the occlusal rest positioning the opposite side of a clasp tip, if we imagine we're going to clasp this tooth, to the saddle area. And we'll come back to that in a little while when we talk about positioning or positioning of occlusal rests to help with problems when designing or providing support and retention and bracing for free end saddles. So we'll come back to this in a little while. Okay, so now we've planned our saddle area. We've decided that it's going to be either a mucosa borne, tooth borne, or a tooth and mucosa borne denture. And now we've got our support drawn on our design. We'll do a few designs in a sec. The next thing to do is to plan our retention, and retention is resistance to movement of the removable partial denture away from the mucosa. So you can think of it as an arrow up. So this is retention. Okay, now when we're providing retention, we automatically start thinking of clasping or creating a path of insertion that differs to the path of displacement, but don't forget we also get retention through the physical forces, so the adhesion and cohesion of the saliva and creating a peripheral seal to get some suction underneath the denture, and we harness the muscular forces just like we would with a complete denture through the occlusal surfaces of the teeth and through the polished surfaces of the denture. So don't forget, it's not just mechanical, which is obviously the talking point of removable partial dentures. It's not just the mechanical retention that provides the retention for the removable partial denture, but this is the talking point. You know all about these physical and muscular forces already, and when we talk about mechanical retention, there are two ways of gaining mechanical retention. Firstly, by creating a path of insertion that differs to the path of displacement. Okay, and in Basker and Davenport's textbook they always have the path of displacement in green and the path of insertion in, or withdrawal, same thing, path of insertion, path of withdrawal, same thing, in red, and we'll use those when we do some diagrams in a little while. So for mechanical retention we can try and create a path of insertion that differs to the path of displacement, and we'll talk about that separately later on, so we'll also come back to that. That'll be the second part that we come back to. A lot of dentures are made with the path of insertion equaling the path of displacement, so the undercuts are identified and blocked out. So we can make our denture such that the path of insertion equals the path of displacement. Okay, and that's quite common to do, and to do that it's very simple, but we must use a surveyor to find any undercuts relative to the path of displacement and block them out so that the denture can come on and off the model and in and out of the patient's mouth. So, for example, if we have this bounded saddle, you can see that there's some undercut relative to the path of displacement. So the path of displacement we always consider perpendicular to the occlusal plane. So here's our occlusal plane. We assume that the path of displacement is at right angles to that, so we'd put this model on the surveyor with the occlusal plane horizontal, look at the path of displacement and find any undercuts like these relative to that path of displacement. Okay, so to do that you need to survey the model. So this is really where surveying first comes in. So to look at the path of displacement, whether you're going to create a path of insertion or whether you're not and you're just going to block out the undercuts, you must survey the models. Okay, so there's one reason why we use a surveyor. We'll come back to path of insertion, path of displacement shortly. So the second mechanism of providing mechanical retention is by providing clasps. Okay, and again clasps go into the undercuts either on the buccal or the palatal aspect of a tooth. So if we have a tooth like so, and we survey the tooth, find the bulbous part here, which is the survey line. The area underneath that survey line is undercut relative to the path of displacement. Okay, here and here, and we can put a clasp arm in that area and gain some mechanical retention relative to that direction. So it goes without saying that for providing clasp we must of course survey the model. So we survey for clasping and we survey for finding undercuts relative to the path of displacement. And then whenever we provide a clasp we must provide reciprocation, and that's because when a clasp engages with a tooth and it's in its fully seated position, here's our molar, here's our clasp arm down here. When it sits in this undercut, when in its fully seated position, the clasp arm is passive, so it's not putting any force on the tooth. When the denture becomes displaced, the clasp arm climbs the side of the tooth. This is the survey line just here, and as the clasp arm comes up it starts to exert a sideways force on the tooth like so. So it's a little bit to start with, a little bit more, and then as it gets to the most bulbous part it exerts a lot of force. And if this was left without anything on the opposite side of the tooth may become mobile, it may get moved orthodontically. And so what we must do is provide something on this side of the tooth, the opposite side of the tooth, to stop this tooth movement, and it makes the clasp more effective and protects the tooth, and we call that reciprocation. So wherever we have a clasp we must have reciprocation. Okay, and we provide reciprocation either by putting a clasp arm on the tooth somewhere on the opposite side, and as the clasping arm rises, so the reciprocating arm, it just looks like a clasp arm but it's on the other side of the tooth and it's passive, the reciprocating arm must climb the opposite side of the tooth and match the force being applied, and that's a very tricky thing to engineer. So so when we've provided a clasp that's going to exert a force on the tooth sideways, we must provide reciprocation to prevent tooth movement. And this is a reciprocating arm which needs to be engineered such that it exerts a force back across the tooth towards the clasping arm. Difficult to do, so an alternative approach or an aid to providing reciprocation is to, on the reciprocating side of the tooth, so here's our tooth again, here's our clasping arm which is going to put force on. What we can do is take an air rotor and put a little flat on the side of the tooth and put our reciprocating arm at the bottom of that flat when it's in its fully seated position, and now as that clasp arm exerts its force it goes up to the most bulbous part, so this reciprocating arm can climb the guide plane and stop any tooth movement. So that's cutting a guide plane for reciprocation. And the final way, or the final reciprocating element that you can design, is rather than having a arm like this, you can design in a plate. So we'd have our tooth, the side that we're going to clasp, and then no preparation required. Got our platal surface here, so here's our clasp arm. This is going to exert force on the tooth sideways, and rather than putting a clasp arm on, we can put a plate down the side of the tooth like so and design that into the connector of the denture. And now as the RPD is displaced upwards, the clasp arm engages, pushes the tooth, and the plate remains in contact with the most bulbous part of the tooth here. Okay, so that's reciprocation, an important part of your design. So now we've looked at the saddle area, looked at support, whether it's going to be mucosa borne, tooth borne, or a combination of the two, designed the footprint of the denture if it's mucosa borne, or considered the footprint of the denture, provision of occlusal rests if we're going to have a purely tooth borne denture, and provision of occlusal rests if we've got a combination. We'll come back to that as we said. And then for retention, we talked about physical and muscular forces, the mechanical retention, and that we can create a path of insertion that differs to the path of displacement, or we can allow the denture to insert in the same direction as the path of displacement. For both of those we need to survey the model to find the undercuts relative to the path of displacement, and we can also provide mechanical retention by using clasps, and clasps engage undercut relative to the path of displacement, and we put our clasp arm in this undercut. In this case, of course, it can clasp relative to the path of insertion if we've designed it that way, and the clasp arm sits in the undercut area, and as it climbs the tooth it's going to exert force on the tooth sideways, so we must oppose that using reciprocation. Okay, so next thing to design into our partial denture then is bracing, and bracing is resistance to the sideways movement of the whole denture, not just an individual tooth where we're talking about clasping, but stopping the whole denture moving sideways. And bracing for most dentures, particularly when they're purely tooth borne, tends to look after itself because the clasp arm sits above the survey line for the most part, and that stops the denture moving sideways, as do the vertical parts of the connectors and the occlusal rests and so on. So it tends to look after itself, but there are a couple of oddities. So for example, when we're providing bracing for free end saddles, these will keep coming up because these are the problem ones. bracing for freehand saddles, we use cross arch bracing, and we'll come back to that when we talk about the occlusal rests for support. Okay, so we're getting there now. Saddle support, retention, bracing, and now we need to think about how we're going to connect all these bits and pieces together, and for that we use connectors, and connectors are either large or small, i.e. they connect the saddle area, so we have major connectors which connect the saddle areas, and they provide the rigidity for the denture. And rigidity is one of the main criteria for a connector. We really want the connector to be nice and rigid and stop the denture flexing. And the other consideration when we're designing the connectors is hygiene, and we need to make sure that we're keeping the denture as hygienic as possible, so we keep the connector away from gingival margins wherever possible. So we want to try and design our connectors so they stay 3 mm away from the gingival margin where we can. And then we have minor connectors, and minor connectors join up the components or connect the components to the major connectors. Okay, and then there are a few oddities that we need to consider in certain situations. So just for completion, you can consider providing indirect retention, and that's for freehand saddles. Coming back to that in a second. And we can do other techniques such as altered cast technique, which we can discuss also. So that's our basic system of design. So starting from the top, working down, putting in your saddle areas, then you go onto your little arrow system, so it's providing support in whichever way you're going to do that, providing retention, so resistance to displacement, providing bracing, resistance to sideways movements, joining everything together with your connectors, and then providing any indirect retention and doing any other technique that you may deem necessary. Okay, so that's it for outlining the system of design. Next I'm going to talk about creating a path of insertion for retention of dentures. So we're sort of focusing on this area here. Okay, so this is surveying, looking at the path of displacement, or going on to create a path of insertion. Okay, so the scenario that we were looking at was where we had a bounded saddle, and we know we've got undercuts mesial to this molar and distal to the premolar, and if we made our denture in the laboratory such that it filled these undercuts adjacent to both of these teeth, we'd find that we had excellent retention but not a very practical denture, because you can't get it in and out. You've actually created a little dovetail joint. Okay, so one extreme, not very practical. The other alternative at the other extreme is to block out the undercut, as you can see I've done on this model, been blocked out with plaster of Paris in this case. So this has been surveyed on the surveyor relative to the path of displacement, and all the undercut relative to that path of displacement has been blocked out. And now we can make our denture so that it drops in and out with no problem whatsoever, and we've made the path of insertion equal to the path of displacement, and an awful lot of dentures are made in that way. Okay, so that's all the undercut's been blocked out on the model. The denture gets produced, and then when this gets fitted in the patient's mouth, obviously there'll be small gaps in between the denture and the tooth where the undercut exists. Now we can do a third option, second workable option, and in this case what we've done is surveyed the model relative to the path of displacement, found the undercut, okay, so the same undercut as on the previous model, but we've decided to create a path of insertion such that the denture slots down the mesial aspect of the molar and engages the undercut. Okay, so on the surveyor what you would do is put this model on horizontally, the surveyor arm comes down, you look for your undercut, and there's undercut both sides. You see this one's already been blocked out, but this is relative to the path of displacement, and then if you decide that you're going to make a path of insertion such that the denture needs to engage this undercut, the model gets tilted on the surveyor until the surveyor arm fits down the side of the molar, or down the mesial aspect of the molar snugly, and then the undercut relative to that path of insertion gets blocked out on the other tooth. And now we make the denture such that it slots in along the path of insertion, so it's going in that direction. The denture drops in that direction so it engages this undercut. So relative to the path of displacement, we've gained some retention on this molar tooth. So here we've gained some retention relative to the path of displacement. We haven't gained any retention relative to the path of insertion, just this path of displacement. So now we've got mechanical retention by engaging that undercut with the body of the denture. So that's going to create some retention for our denture, which is going to be permanent. Okay. It does mean that you'll have a larger gap here, distal to the premolar, because we've had to block out the undercut relative to the mesial of the molar. Okay, so there's going to be a gap when this denture gets fitted in the patient's mouth where I've blocked out the undercut distal to that premolar. So when we want to do this then, when we want to survey our model, we first of all survey relative to the path of displacement. Okay, and on our model just there we had the situation where we had the premolar like so, and the molar here, and when we survey this, put our surveyor arm down the side, we see that there's undercut relative to the path of displacement. Remember, the path of displacement is always at right angles to the occlusal plane, and we can utilise this undercut, or we can just simply block both out. So if we block both out, we have a path of displacement which equals the path of insertion, or we can be smart and we can decide to utilise some of that undercut. So we can, same scenario, we can take our surveyor arm, find the undercut relative to the path of displacement, like so, tilt the model on the surveyor and survey relative to the path of insertion, or create a path of insertion so that the denture is going to slot down this mesial aspect and fill all this area here with denture. Okay, and then when we do that, all this area here needs to be blocked out, and then we put our teeth on like so. And now we've created undercut, and now we have gained retention by engaging this undercut mesial to the molar. Okay, and this is now our path of insertion down in this direction. Of course, when we had our situation here where we've got the path of displacement and we've just blocked out the undercut, our denture would fit like so, and it would just contact the contact points here and here, and there'd be gaps either side of the saddle area. So that teeth would go on something like this, wouldn't they? Yeah. So this is with the bounded saddle. In practice it's quite difficult to achieve because we're not just dealing with one saddle area, we're often dealing with 2 or 3 saddle areas. So it's quite tricky to create a path of insertion for bounded saddles. Can be done though. There are a couple of situations where we create a path of insertion by default because it's a very simple thing to do. So for example, when we have free end saddles, so there's going to be undercut distal to these premolars, so we can engage that with our denture. So